sections 3.1 and 3.2. So in chapter 3, we start off talking about summarizing symmetric distributions. And now we will be working with numerical variables really from here till the end of the course. One other section, we'll talk about categorical again. Okay, so if you remember from chapter 2, distributions are described by mentioning their shape, their center, and their spread. Okay, so for symmetric distributions, of course, every one will have a shape that we would say is symmetric. The measure of center will be the mean, or what we commonly call the average. And our measure of spread will be something that we call standard deviation. So when we want to describe a symmetric distribution, we would say its shape is symmetric. We would give an actual value for its measure of center and also an actual value for its spread or measure of spread. Okay, so let's talk a little bit more about this. When we want to talk about center, and we're going to use the mean for a symmetric distribution, there's two ways really of thinking about the center. We can talk about the balancing point, or we can talk about the halfway point. So when our distribution is symmetric, the idea of balancing point is a better description of our center. When we work with the skewed distribution, we'll see then that the halfway point is a better measure for center. All right, so if we wanted to visualize the mean, if we had a distribution, and of course we can see this is symmetric, it's unimodal, right here would be our balancing point, okay? Or this is where we would find our mean value. If we want to calculate the mean, we find the average, which is not a hard process. You've probably done this since grade school. If our sample of data were these 5 values, then in order to find the mean, we would simply add them all up and divide by however many there are. So we would just simply say 3 plus 12 plus 9 plus 10 plus 6. And then we would divide that by 5 since we have 5 data values. And that gives us 30. Oh, I'm sorry, that's a 40. Add those up, we get 40 divided by 5, or a mean value of 8. Okay, not a hard process to find the mean. Okay, before we talk about our standard deviation, we need to go over some terminology. Statistics has its own little language of words, but also symbols. So if we wanted to talk about the mean, if we're referring to the mean of an entire population, then we call it a parameter. If we were talking about the mean of just a single sample, then we would call it a statistic. So we have population parameters and sample statistics. Kind of easy to remember. SS, P, and P there. All right, so the symbol that we use for a population mean is this Greek lowercase mu. If you wanted to spell it, it would just look like that, mu. For our sample statistic, we call this X bar. So it's an X with a bar over it, or pronounced X bar. For our standard deviation, which we will get to very shortly, in a population, we represent it with this lowercase sigma, another Greek letter. The standard deviation of a sample is simply a lowercase s. If we're referring to the size of a population, we use a capital N. the size of a sample, we use the lowercase n. Okay, so these are different symbols that we will use throughout the course. An important fact to remember, parameters are set or fixed for a given population. They never change if the population doesn't change. So we say parameters are fixed for a given population. But with statistics, it's a little bit different because these come from the samples. And each time you draw a different sample, you're going to get a different sample statistic. So whereas parameters are fixed for a given population, statistics will vary from sample to sample. And that makes sense. If you keep drawing different samples from a given population, the population might not change, but you'll get different values in your samples. Okay, moving on. So we have a formula for the mean, even though we know how to find it. And it looks like this. So if you've looked at your formula sheet, you've probably seen this. This symbol is also a sigma. It's a Greek letter, but it's a capital sigma. Okay, anytime you see this capital sigma, it means summation. Okay, so capital sigma, you think in terms of adding. So that's really what we're doing. The formula for our mean, our sample mean of X bar, we say it's the sum of all the X's divided by n, the sample size. Okay, so the formulas might look a little strange, but they're not too difficult to understand. So here's the formula where this symbol, this capital sigma, means the sum of X is a data value. And N is the sample size. So here's our first formula, the formula for the sample mean, which we're calling X bar. So an example, if we had this sample of data and we wanted to find the mean, we would say X bar is equal to the sum of each X divided by the total number of values that we have in our sample. So in this case, of course, it would then be 34 plus 12 plus 15 plus 19 plus 38 and so on until we have the sum of all of our data values. And then we divide it by the total number of values that we have. So in this case, we have 10. Sorry, lost track of counting there. Okay, so if we added it across the top, we get 272 divided by 10, or that gives us a mean of 27.2. So if your data set is small, it's not hard. You just pop these numbers into a calculator and divide. If it's a large data set, you might not want to do all the adding. So you can use Excel. And I'll show you that now. We'll switch to an Excel screen. And some of you might already know how to do this. So what I've done is I've listed the data values. If it's a large data set, you could probably copy and paste it all into a column. Okay, once you're in there, then you click on an empty cell. So I'll click this one over here beside average, because that's what we're going to find. Right, so across the top, if your version of Excel has this, you would click on formulas, and I'll show you. If it doesn't have this, I'll show you exactly what to do. So when it comes up formulas, you're either given this option to click on more functions. If that's not there, then you click over here where it's f of x, insert a function. Okay, I'll do this method first, then I'll show you the other. So more functions, and we choose statistical. We're working with statistics functions. And you just go over to the drop-down menu and click on average. You'll see a pop-up window, and it'll say number. So they're asking you, what numbers do you want to average? Now, if you only have one column of data, it will pop that column in for you. If you have more than one, you're going to have to choose it. So what you always do is you go over and you highlight your column of numbers. And then you come to your box over here and you say, okay. And it gives us our average, which we already knew was 27.2. A shortcut, if the only thing you need to find is the mean, you can just highlight this column of data and then look across the bottom, and I hope you can see this on your screen. It'll give you the average, the count, and the sum. So that's a short way, but you can always use this function, the average function. Okay, then I wanted to show you the other way. If you don't have the choice for more functions and you use the f of x, when you click on it, you get a pop-up window. If it's not set to statistical, there's a drop-down menu. Some of your computers will just be set to most recently used. And if you're only using this for statistics, then you're good. But otherwise, you should choose statistical. And then again, we have the same idea. It lists the functions, and here we choose average, hit OK. And now we have the same drop-up or pop-up window. Excuse me. And then the same thing. You highlight the column of numbers that you want to average, and you click OK. And again, we get the same. All right, back to the blackboard. So that's how you can use Excel to find the mean, or you can just simply add your data values. All right, now we're ready to talk about the spread or the variation. For a symmetrical distribution, we call this standard deviation. So the official definition, standard deviation, it's the average distance from the mean of all the data values in a distribution. So we're saying, how much does each of these values vary from the mean on average? Well, how do we find this? Well, if we're talking about an average distance, we tend to think, oh, that's a mean. So we should find the mean. And now we want to subtract to see how far away each of our data values is from the mean. So we would subtract the mean from every data value to find its distance from the mean. And then we'd add them all up and divide. That's our process for finding a mean or an average. Well, let's try an example, a very small data set, 5 numbers. If we wanted to do the first step, we take our data values, we add them up, divide by 5, and we get a mean of 4. Well, then the next step after that, we should be subtracting 4 from each of our data values. So if we do that, let me see if I can scroll a little bit more. There we go. We can take 2, our first value, and subtract 4. Well, that gives us -2. And 3 minus 4 is -1. And 4 minus 4 is 0. 5 minus 4 is 1. And 6 minus 4 is 2. So if we take all of those differences and we add them up, we get 0. Every time you will get 0, because it's the nature of the mean. The arithmetic mean of a set of data is that one that's exactly in the middle distance. So if you have this many points below the mean and this many points above the mean, these will always cancel each other out. And so then that would tell us, oh, if we were trying to find the standard deviation, we'd always be taking 0 divided by some number. In this case is 5, and we say the standard deviation is 0. But we know that's not true because the mean is 4 and the average distance can't be 0, or they would all be 4. So we have a problem. Well, the way to overcome that is, instead of just taking the distance that each point is from the mean, we can take that distance and we can square it. Because when we square a value, it always turns into a positive number. So you have to square the differences before we actually add them. So in this case, you can see, I've done this, 2 minus 4, that's -2, but when I square -2, I now get a +4. And when I square -1, it's now a +1. And of course, it doesn't matter. 0 is 0, no matter if you square it or not. And then here I get a +1, and I square it, and I get 1. And I get a +2, and I square that difference, and I get 4 again. But the only problem is, we now have square units. Remember, these were just initial values. These were measures in inches. So something was measured, and these are the inches that each of these came out to be. But if we square this, now we have square inches. So we need to do something. Well, the idea is, once we follow the process, then we take the square root of it. So that's how we get the formula for finding standard deviation. When we're looking to find the standard deviation of a sample of data, it's actually going to be the square root of the sum of each x value, so that's x, minus the mean, that's our x bar, and we square it. And then we divide by, now this is going to sound strange, but we don't divide by n, the number of values. Mathematically, it's been proven that you get a better value for standard deviation if you divide by n minus 1. Now, the reason for this, the proof of this is, it really belongs in a course that's more advanced than this course. So I'm not going to go through all of that. I'm just going to tell you, this is our formula for finding standard deviation. Okay, where? And I'll always give you the where so that you understand what each of these terms are. S is our sample standard deviation. And then we have X is a data value. Of course, X bar is our sample mean. And N is the sample size. So this is our second formula, sample standard deviation. Again, it's the sum of each data value minus the mean, that quantity squared. And then once we add all those squared differences up, we divide by n minus 1, the sample size minus 1. And in the end, we take the square root of it so we can get back to the original units that our set of data is in. All right, let's try an example. So here we have, again, a small sample of data with just 1, 3, 7, 9, and 10. And we're now going to find the mean, X bar, and the standard deviation, S. Okay, X bar, not too hard. we add them all up and divide by however many there are. Okay, but again, I wrote the formula so that you get used to seeing the terminology. So when we go through and we add these all up, we get 30. We divide that by 5, and that gives us a value of 6 for our mean. For the standard deviation, okay, this takes a little bit more work. So that's why I use just a small sample of data. Okay, and if you saw in the weekly module that you're going to have an emailed homework example that you have to send back, it's going to be a problem where you're going to take a set of data, small set, find the mean and standard deviation by writing it all out according to this definition of standard deviation, and then you'll email it back to me. Okay, so back to this example. If we want to find our sample standard deviation, it's going to be the square root. Now I'll make a big one, because we're going to add up the sums, or the, I guess I should say the differences of each value and the mean squared. So it's going to be 1 minus 6, and that's squared, plus, okay, our second data value is 3. 3 minus 6, that's squared, plus 7 minus 6 squared, plus 9 minus 6, we square that, plus 10 minus 6. And we square that, and then we're going to divide it by n, which is 5 minus 1. So I'll write that out, 5 minus 1, because that fits our n minus 1. So if we continue on, let's see if I left enough room here. 1 minus 6 is 5. 5 squared is 25. Plus 3 minus 6 is negative 3, but negative 3 squared is 9. Plus 7 minus 6 is 1. 1 squared is 1. Plus 9 minus 6 is 3. 3 squared is 9. And 10 minus 6 is 4. 4 squared is 16. And it's all of that divided by 4, our 5 minus 1. Okay, so in the end, we get the square root of 60 over 4, or if we wanted to simplify that further, the square root of 15, or 3.872983. I think that was all the value, that was all the places I had on my calculator. So in the end, then we could say we have a sample mean of 6 and a sample standard deviation of 3 point, if we rounded to 3 decimal points places, we'd say 873. The 9 causes that 3 to go up to a, or causes the 2 to round up to a 3. And so there we have it. Okay, this is how you find standard deviation according to the definition. All right, but we could have done this exact same problem in Excel, and I'll show you that here very shortly. But before I do that, I want to point out again, as I said, you'll have an emailed assignment this week. So it's not going to be in my labs. I'm actually going to send you an email, which you should already have gotten by the time you watch this video. Okay, you'll get a set of data, and then you'll have to find the mean and the standard deviation. And then you can take a picture of it or screenshot, however you do it, and send a copy of it back in an email to me. Okay, and then, so you should be looking for that. And then I'll say it now, there's bonus points available for submitting this assignment by a certain date. And I'll tell you that in the email. All right, so how would we do a problem like this of a data set that consists of 5 values, 1, 3, 7, 9, and 10? How would we find that in Excel? Well, let's go there and I'll show you that now. Okay, so say you you just opened a blank Excel screen. So let me clear everything out of here. So we'll start from scratch so that you're going, okay, now what do I do? All right, as I said, pick an empty cell. Never click on a cell that has data in, you'll get an error message. And we don't have any data, but we can easily type that in. 1, and then 3, 7, 9, and 10. All right, so a small set of data, and we want to find the sample standard deviation. So we can go up to formulas again, more functions, statistical, and then scroll down until we see stdev.s for sample standard deviation. So this means standard deviation, and this says .s for a sample. Okay, but I won't use that pop-up window there. I'll use the f of x function this time. So over here, we're on statistical functions, and now we scroll down the same until we get to the standard deviation.s. And I'm showing it this way because if you're using the version of Excel from the school, you'll have to use it this way. Okay, and then we hit OK. And it says number 1 and number 2. We're only doing the standard deviation of a single value data column. So ignore the number 2. So they want to know, what numbers do you need the standard deviation of? Well, we just highlight those columns. Oh, I think I clicked in a wrong spot. Let me cancel that. No, I'm in an empty cell. I'm at cell number 6. Usually I try to do it off to the side, away from the data column. All right, so again, insert a function, statistical. If I chose this most recently used, then you see the function that I just picked is at the top. So that might be better. Maybe it's shorter for you, and you just hit OK. Okay, so they want to know, what numbers do we want the standard deviation of? It's this column. So I'll highlight it, and I'll come over here and say OK. And there we have it. Same answer, 3.87298. Much easier than working everything out. However, for this first homework assignment that you're going to email me, and it's the only one that you'll email me the entire semester, I want you to work it out just like we did here. Show me all your work, your differences squared, and your actual answer. All right, moving on. Section 3.2, we talk about this empirical rule. Okay, now this rule applies to unimodal and symmetric distributions. And it'll make more sense as we start working with the normal distribution. I think some of you recognize the bell curve. What this rule says is that if you have a unimodal and symmetric distribution, 68% of all of your data values will lie within one standard deviation of the mean. Okay, so that's a large percentage of all the data values. Well, here, 95% of all the data values, I'm just going to put these little quotes, will lie within 2 standard deviations of the mean. And then nearly all, and soon your book will tell you it's really 99.7%, which is nearly all of the data values within your distribution. They'll lie within 3 standard deviations. Whoops, let's make that a 3. 3 standard deviations of the mean. So if you had 100 data values, 95% of them would be no more than 2 standard deviations away from the mean. And nearly all of them would be only 3 standard deviations away from the mean. Okay, I like to draw the picture of what this means. And of course, this is a future picture. This is an example of a standard normal curve. You don't really have to know that now. You'll become very familiar with this. So on the standard normal curve, it has a mean of 0. So if we were talking about a population mean, we'd call this value in the center mu. And if we were talking about a sample mean, we'd call that x bar. So what it's saying is that 68% lies within one standard deviation of our mean, meaning one standard deviation above or one standard deviation below. So that's 68% of all your data. But since this is a picture of the distribution, you can see the highest frequency of values are right around the mean. It's where our curve peaks. Okay, if we move out to 2 standard deviations, then we're saying that's where almost 95% of our data values will be. So if we had 100 values in our data set, 95 would fall between these 2 markings of 2 standard deviations below the mean and 2 standard deviations above. And then the third part of the empirical rule, we say nearly all will fall within 3 standard deviations. And we'll begin to see as we continue on that values that fall outside of 3 standard deviations, meaning they're pretty far away from our mean value, we'll think of those as outliers. Okay, but that comes in the future. If we were talking about the mean, and we didn't put a 0 here, the mean of a population, we would call this 1 sigma, 2 sigma, and 3 sigma. And of course, on the other side, we'd call that -1 sigma, meaning 1 standard deviation below the mean, -2 sigma, and -3 sigma. If we were talking about a sample mean, then this would be S, 2S, and 3S. And to the left would be -1S, -2S, and -3S. Okay, so this is really a future picture, but it's a way to understand by looking at this curve. You can see the majority of all of your data values lie under the curve between 3 and -3 standard deviations. All right, so let's try an example using our empirical rule. It says from a unimodal and symmetric sample of data, so we know that the empirical rule will apply. We find the sample mean to be 55 and the sample standard deviation to be 8. And the question, what we want to find is, it says 95% of all the observations in the sample lie between what 2 values? All right, since it's a unimodal and symmetric sample of data, then we can apply the empirical rule. And according to the empirical rule, 95% of all the data lie within 2 standard deviations of the mean. So what that looks like symbol-wise, we're saying that it's X bar minus 2 standard deviations all the way to X bar plus 2 standard deviations. Well, we know that the standard deviation of this sample is equal to 8. So 2 standard deviations is just going to be 2 times 8, or 16. And we already know that the mean X bar is 55. So if we wanted to find between which 2 values that 95% of all of our data values will be, we just fill in the blanks here or match up. So this is going to be 55 minus 16. And this one will be 55 plus 16. Because 16 is our 2 standard deviations. If one is 8, then 2 of them would be 16. So in answer to the question, they wanted to know between what 2 values will 95% of all the observations or all the data values in our sample lie. we can say between 39 and 71, because 55 minus 16 is 39, and 55 plus 16 is 71. So there's the answer to our question. So without even knowing what our data values are, or not even knowing how many there are, we can say we know for sure that 95% of all the data values, all the observations in the sample will lie between the values of 39 and 71. All right, the last thing that we want to talk about is the idea of a z-score. Okay, so really a z-score is just an actual measurement converted into a standard unit. I like to think of it as comparing apples to apples. If we are comparing measurements and one group was measured in centimeters and another group was measured in inches, it's kind of hard to compare because we're not using the same units. But if we standardize a value, it actually eliminates the units and we give it a standard score or a z-score. The way we find z-scores, we take an actual value, we minus the mean, and then we divide it by the standard deviation from the data set that it came from. Okay, so if we wanted to use symbols, our z-score is always going to be an actual value, which is x, minus our mean, we're using a sample, so that's minus x bar, divided by the sample standard deviation, or S. So here's our third formula in this section. How do we find a z-score? It's an actual value x minus a sample mean x bar divided by the sample standard deviation S. Some things to remember: positive z-scores are above the mean and negative z-scores fall below the mean. Okay, if we were thinking in terms of that curve. So a z-score is really, and this is important, it's the number of standard deviations above or below the mean. So when we talk about your tests that you take, the ACT or the SAT, your scores aren't given as actual percentages, they're z-scores, really. Okay, so a z-score that equals negative 1.2, we say it's 1.2 standard deviations below the mean. And a positive z-score of 2.4, we would say that's 2.4 standard deviations above the mean. Okay, so as I said, a z-score is simply telling you the number of standard deviations that an actual value is from the mean. And z-scores are good to use because it's like comparing apples to apples. When you have different measurements or even different groups, it's best to have a standard score for comparison. All right, so we'll finish with an example. It says Maria scored 80 out of 100 on her first stats test and 85 out of 100 on her second test. So if we look at that strictly percentage-wise, she got an 80% on the first test and an 85 on the second test. But now they want to compare her test values with the class. So on these tests, the mean for test 1 was 70 and the standard deviation was 10. And then on test 2, the mean for the test, so the average score of the class was 80 with a standard deviation of 5. So we want to say, which test did she do better compared to the entire class? Okay, not just her score. If we're just using her score, we can see she got an 85 on test 2, 80 on test 1. She looks like she did better herself on test 2. But compared to the entire class, on which test did she do better? Well, the only way to compare that is to convert each of her test scores into a z-score or a standardized score. Okay, so we can just call it Z1 for her first test score. And then we'll find out what her second test standardized score is. So we'll call that Z1 and Z2. All right, the formula is always going to be X minus X bar divided by S. So in this case, her actual value on her first test was an 80 minus the mean, the average on test 1, X bar was 70. So minus 70 divided by the standard deviation for test 1 was 10. On test 2, her actual score was 85. And the average on test 2 was 80. And test 2 had a standard deviation of 5. So the scores were a little closer together, not as spread out because your standard deviation was smaller on test 2. So if we go over here and we calculate this, 80 minus 70 is negative 10 divided by 10, we get a standardized score of negative 1. So on her first test, she was 1 standard deviation below the mean. If we come to test 2 and we subtract 85, I'm sorry, why I did negative, I have no idea. It's not negative. And she didn't do below the mean, she was above it. 80 minus 70 is 10, 10 divided by 10 is 1. Then we come over here, 85 minus 80 is 5 divided by the standard deviation of 5. Once again, she had a z-score of 1. So just in herself, comparing to her own scores, she did better on test 2. But compared to the entire class, she did the same. She did equally well on both tests. So that really would be the answer. She did equally well on both tests. And how do we know that? The reason? She had a z-score of 1 on both tests. So standardized scores are really used for comparison. If you have nothing to compare to, then there's really no reason to standardize a score. Okay, if we're just looking at the standard deviation of each test, and I mentioned this briefly, on test 1, the standard deviation was 10. There was more variation in scores. But in test 2, the standard deviation was only 5. Okay, so it looks like the scores on test 1 were a little less consistent, farther away from the mean. Okay, so this is another way of thinking in terms of standard deviation, consistency. Okay, the scores were more consistent on test 2. Whoops. And the reason why? The standard deviation was lower than on test 1. So the smaller the standard deviation, the more consistent we say the data set is. Oh, and I guess I should spell consistent right. An S in there, consistent. Okay, this ends sections 3.1 and 3.2.